let's go. Okay. Let me see where we left off. We just added triangles. So we're going to go through and largely focus on winding order today, and maybe do a couple of other to-dos in the code. One of them that we noticed last week, if we scroll down to down to here, was like we have this did intersect test, and that's really a great opportunity to do an early out. I think all we have to do is this. And, you know, if we were being pedantic about it, we could do like no intersection, and then like stick a semicolon in there and get rid of that, and be like, go to no intersect. So we could do that, but I think we'll just leave it as this for now.
Go-tos are evil.
Oh, absolutely, so evil. This, what a lie! What a lie people have been told. There's also, we could at some point go through and redo our drawing code to actually draw this stuff, but I'm not entirely convinced that's worth the effort. Basically getting this stuff and copying it back to the drawing code to make it work. But I don't know. How do you feel about that? Do you think that's worth our time, or should we?
Probably not on, maybe not on air time. It might be something worth doing later, but I think that's a lot of a lot of messing about.
If you find yourself some time to do some off-stream stuff, that could be a homework as an option. So the next thing that we wanted to do was, so there's a few things we could look at. We could get rid of that allocation, but that's actually kind of fiddly, so we'll skip that for now. So we'll move on to the winding order stuff, and that'll let us do things like area of a polygon, because you can see we've got all this think about winding order, so we're going to think about that. The first thing we need to think about is the fact that if we have a shape in our current coordinate system, which is y is down, and that shape looks like this, let's say, and then we flip our coordinate system to y is up. The same shape in each coordinate system, you can imagine, would be something like this. And we've just flipped it around. So if this is one, let me use a different color. If this is 1, 2, 3, then this is 1, 2, 3, and you can hopefully see that, you know, this one is winding counterclockwise, and this one is winding clockwise.
Yep.
So that's pretty straightforward, pretty simple. Now, when I was testing this, I noticed this is actually going to be pretty simple. We have this get camera method, and we want to have a camera that takes our world space into client space, basically. So, you know, we've got a happy little window with its happy little title bar, and it's like, you know, this is Y and this is X. Whereas what we want is something like this. Browser window. So if we have something like this is like the Cartesian coordinate system, which is, you know, mathematically standard. And so one of the main reasons we want to use a system is if we're like doing something, like if we're copying some formulas or something, it's just so nice to have it this way up. It's nice to have gravity that's, you know, goes in the negative direction, and so on. It's also nice, let me see, if we have like when we're thinking about polar coordinates, so angles, it's nice if they go counterclockwise in the positive direction. So basically we just want to follow those mathematical conventions. So we want this one, and we want you know, theta to go that way. If we have this system, you can imagine the same flipping thing occurs. So positive angles in this system go this way, which is not the standard. So we're going to flip that around, and that is as simple as sticking a negative symbol right there. So now, what's going to happen when we do this? So, I mean, we can have a little think about, like, you know, where does camera get called? It gets called in a couple of places. And one of the things, it gets called here to actually do the drawing, but it gets called here, and you can see right underneath it we're doing a get inverse. So we don't even have to worry about how we're going, you know, back from screen coordinates to like world coordinates, because we've already done the work here with this get inverse function, so that's handy. What's going to happen, however, when we run this sucker is, you know, you'd think stuff would appear on screen, but can't see a damn thing. So if we go over to line batch, and basically we've run into this issue that all of our winding orders are backwards, and we've got backface culling turned on. So if we go graphics device down here, raster state equals sort, we turn off backface culling, and then we try it. All of our lines come back, and you'll notice the triangles are flipped the other way around now, but it still works. Yes. Sorry, I've gone over that.
I don't. No, it's just I don't quite. I don't at all understand what you just said. So when you talk about, so there was a default here. Clearly, the default.
So let's put the default in. The default is cull counterclockwise. And so that...
Yeah. So I remember when we talked about winding order,
so
culling occurs.
Okay, so let's say we have...
Is it because it's trying to... this is review, and you're about to tell me, but it's just basically... it's trying to remove the vertices that we wouldn't see because we're assuming a certain projection, and if it's depending on the winding order, we those things redundantly.
Pretty much. So not vertices, but faces. So you know we have
right.
This guy. We want to see these faces, but you know the ones here, we don't want to see. And this is kind of tricky to show in 2D, but you can imagine that all of these faces, like these ones that we can see, their winding order is going to be clockwise relative to the screen. And as this rotates, as this shape rotates, so this one panel, like this one, you know, it becomes more oblique. Like that, it's rotating around, it's still clockwise, but as it, you know, as it flips around to like this way around, as it rotates, this suddenly becomes counterclockwise. relative to the screen. So the vertices are still in the same order spatially. You know, it's like 1, 2, 3, 4, 1, 2, 3, 4, and then they've flipped around. It's like 1.
Top right.
Yeah, so yeah, 2, 3. So now they're going counterclockwise, even though they're the same vertices. We've just changed the angle we're looking at them. So that's a really like neat trick that the GPU uses to figure out. It's like, oh, this thing's facing away from the camera. Let's not draw it. And so we probably want to actually maintain that default. So, you know, we could be like, all right, well, instead of counterclockwise, clockwise, and then we get our drawing. But it's probably a more sensible thing to do to just, I know you just typed that in, but if we remove that and actually just change the vertex order up here, so you recall this code was basically this draws 6 triangles like this, and it says, all right, this is 1, 2, 3, 4, 5, 6, 7, 8. I'm kind of making up these numbers, so don't exactly quote me on that. And it's like, all right, give me 1, 2, 3, give me 1, 3, 2, give me that, give me that. So that's how the indices system works. And so if we just want to flip around these triangles, all we have to do is pick 2 of these vertices and change which order they appear in. So if we come up to here, all we have to do is like, all right, this is the first triangle. If we change 0 to 1 to 0, 1, 2, we flip the order of that one, and I mean we can even run it and we can see, oh look, one of the triangles has appeared. So if we keep going through, so 1, 2, 3, 1 becomes 2, 1, 3, and so on. 3, 4, 3, 5, 5, 6, and 5, 7. So in theory, and now we have that back, yet we're still using the same default winding order. So that's seems to be the convention. I don't actually think there's any. That's not good.
0, 1, 2, 2, 1, 3, 2, 3, 4, 4, 3, 5.
Well, is that a bug?
4, 5, 6, 6, 5, 7. I think this part is okay. I must have some other thing.
0, 1, 2, 2, 1, 3. Yeah.
See. Yeah. So then I guess I put her in though.
You flip the camera, so
that is.
That looks fine. So what happens when you run that? Is it still?
It's just empty. Yeah.
Okay. Well, it might be time.
I may have forgotten what we were when we were specifying the call. Yeah, I don't have anything on screen.
Okay.
Specifying the call. Where was that?
Well, possible. Oh, that's really weird. So we removed that line of code, but
Oh, line batch finish. Yeah. Just double check that I did actually delete that line of code. Yeah, I did.
I mean, well, try putting it in explicitly, because perhaps there's some other bit of code in your version of the source that actually is setting it.
Oh no, raster state, and this would be back to the default.
Yeah, so raster state.call counterclockwise.
Computer's really slow today. Nope, nothing. What did I do?
Okay. All right. That's no good. So my recommendation at this point would probably be to back out changes.
Yeah. Well, I'm just
we haven't actually changed that much. So if you just undo everything.
The changes. I made a negative there.
Oh, you got version.
I've got. Yeah, line batching there. Oh yeah, I couldn't do my thing. I'm not, this is not be something silly in here, but this is going to be all the changes since we did winding R, which tells me that the issues in physically. Let me just see what the last couple of changes were. I did the early out. That's it, early, actually. So, I don't know. I think it was working though before we started, so there, like you said, there's probably the safest bet is to just get rid of all my changes. Oh wait, no. Get rid of all of these changes. And just start over. Actually, that's probably fine. I don't need to write that again. Let me just see where I'm at.
Let's just see if we can get this thing displaying again, because yep. So it displays that now, so that's a great start.
So I have to do is just this again.
So it should be a case of
1 2 2 1 3 2 3 4 4 3 5 4 5. Whoops. 6 and wait a minute. How come I saw something when I did the I did the so did was you changed the this zoom. You changed the zoom to negative zoom and then couldn't see anything, but I could see something even though negative zoom. Like really? I'm like flip. I think so because
let's
only at this point.
Let's try it. Let's just run that code. We'll see. Isn't debugging fun?
Yes. Yeah, I can't. It's gone now.
Okay,
yeah.
So if you flip the zoom around now, you didn't have zoom flipped already or something, did you?
I don't know. It was zoom before, and now it's zoom minus zoom. So let me just remove.
Well, I mean, yeah. Try flipping zoom around and seeing if it is a backface culling issue.
Yeah. So zoom is gone. I mean, it's the way it was before. Nothing. This is bizarre.
That is very bizarre.
It's rare. The only are this line batch. That's it. So that seems
okay.
Wrong.
So let's go through your code and just check where the camera is ending up. This because this is what we changed here. I'd recommend also maybe going into line batch.
Oh, I see. There's two silly get cameras. There's a chance that I only changed.
You have two get cameras.
Well, I could the old imgui. So let me just delete that, and that'll help a lot. I think.
Oh, you were in the wrong file.
Yeah, I think I was in the wrong file.
Okay.
The physics game. Yeah, that makes it starting to make a lot more sense. The line batch, nothing has to change, and then physics game. Get camera minus zoom. Let's see how we do now.
Okay, mystery solved.
Well, yeah, for sure. Although I thought my triangles are in the wrong direction compared to yours. Are they not?
No, they're now correct because this is right? This is why it's good to settle on this fairly early in the piece, because we have what you could call a bug in our code. If we scroll down to, and hopefully this is the only instance, well, this one too. Hopefully this is the only real instance of that, and that is here where we're like top left is negative. Yeah, so all of these plus minus here, really that should be plus minus plus minus to go top and bottom.
Oh, I see.
Because obviously we flipped it, and yeah. So this is why it's helpful to land on this early and just stick to the convention, because otherwise you end up in this sort of situation. So there's other instances of this code, but like maybe we'll fix up draw rectangles so it's not going to bite us later. So And I'm thinking at this point, because it's all commented out, this is probably getting kind of stale, this code. So we could, if we're feeling a little bit reckless, we could go and just grab all of this commented out stuff and be like, goodbye.
That's what source control is for.
Yep. Yeah. I was like, I don't have this in source control.
Oh, you don't need to. All right.
My source control is going to you and be like, Daniel, I broke it. Can you email me the code?
All my stuff's it's on.
Oh yeah, it is too actually. Okay.
Okay. So yeah.
Mystery solved. We've just deleted a whole lot of code, so now you can see like our drawing method actually fits on screen just about, which is nice. So let's go back and let's go through this now and be like all of the places where we're like think about winding order, and we'll think about it. So what we probably want to do is, we established that the default is, clockwise polygons get displayed and counterclockwise ones don't. So why don't we stick to the convention that the graphics library uses and be like, oh, just make all of our valid polygons clockwise. So top left, top right, bottom right. Top left, yeah, hang on. Top left, top right, bottom right is clockwise. So that's fine. We don't even need that comment. Then we scroll down and it's like, okay, get polygon axes to do think about winding order. So now we've actually, we haven't just guessed what the winding order is, we can actually specify it. And so we specified that it was clockwise, which means that our shape is 1, 2, 3. So it's basically that, and then that, and then that. And what we're doing is we are rotating rotating and normalizing to get our vector. So if we rotate counterclockwise by 90 degrees, counterclockwise by 90 degrees, we get, a vector coming up this way. And if we normalize that, we get a normal for that axis. So you can just imagine this, that is the normal for that particular thing. So what we want is a rotation of 90 degrees. And we've got perp 270, so it's like, that's now a bug. So let's change that to 90. And hopefully that explanation made sense.
I was with you up until, well, this is the normalization you were talking about.
Mm-hmm.
And then perpendicular is it's because it's, well, in that case, you said it's counterclockwise, but...
Well, let's
I thought we were thinking... No, that's right, yeah, no, if you go back to your layer there, drawing.
Yep.
This is just for me.
My questionable
it was clockwise, but then I guess I'm just lost on. I get 90 degrees is 90 degrees is for counterclockwise. In other words, like those blue arrows.
We're taking the polygon is clockwise, but we're taking this one here and going counterclockwise to get this one here.
Now what? But see, that's the part I don't understand. I guess like why are you able to say that? Like,
well, you can imagine if we had the opposite shape. If we had the shape that was going counterclockwise, that would be like 1, 2, 3, and so if we took the in order vertices like 1 to 2, or we'll use that one to get the the arrow facing outwards.
Right, because the arrow needs to face outwards. That's what. Yeah, that's from yesterday or last time. And it has to face outwards because we found if it was facing inwards.
In fact, it actually doesn't matter in this case. But it's, again, this is like one of those convention things. So I'm kind of setting something up like for future use, basically, because like the fact of the matter is we just need this axis, and if we're getting like negative values here or positive values here, it doesn't really make that much difference for the separation algorithm. But if we're like and even in this case, I don't think it's going to matter, but there are cases that occur where it's like, give me the I'm trying to think of, I've blanked on when this actually applies, but it's like, give me a direction pointing outwards versus give me a direction pointing inwards, and we need to know that. So yeah, the convention is always that normals point outwards. You can imagine if you've got like a geometric, bit of terrain or something, you'd want to know, say, all of the directions pointing upwards. And this has effects for things like lighting. Because you want to know if you've got let's use like yellow for a light. If you've got like a happy little sun here, you want to know, okay, the sunbeam goes down there and it bounces off that to the observer, and to get that bounce direction correct, you need that normal to be pointing outwards. Otherwise,
cool.
It breaks. Yeah. Depending on the algorithm.
Yeah, that makes sense. And yeah, I get why that, like, we have clockwise winding order, but you were taking that first vector and trying to get the normal.
Yeah.
And that's why it's perp 90, because it's on the outside and you have to face up, which is counter to the winding order, therefore perp 90. Okay, I'm good now. Sorry.
No, that's all right. So if you come down to the draw method, we can like really quickly slap something together that I think is worth doing, just to demonstrate this. So arrow. If we change our line to an arrow for a second, we can be like, look, there's our winding order. We can see it. We can prove that it's counterclockwise, and we can go so far as to be like, I'm just going to bang this in because I'm going to delete it immediately anyway.
No, I'm not going to type it then.
Yeah, there's so what I'm doing is to C equals. So what I'm doing here to get the C, as in the center, is I'm just taking the two sides of the line and I'm averaging them to get the center of that line. So does that should make a lot of sense?
Yep.
And then I'm just going to do the same thing as we had up there. So and so this will show that v dot perp 90. So that's the code we had before, and if I run that, you can see we've now got our normals. And if I as that should give me the normals facing outwards. So does that make a decent amount of sense?
Yeah.
So that's a handy thing to do. This is the sort of thing I did when I was like learning this. I guess it's like, oh well, we'll just draw everything and make sure everything's correct. So, but now it's like fairly ingrained. So that's all good. So line, send that back. Okay, so we have our winding order. Is there any other places we need to fix that up? So we had get axis, so we sorted that one out. Area of a polygon we're going to have to go and have a look at. I think that's all of the places where we had to do with winding order. So This is where winding order becomes relevant. So let's do a little bit of maths. Are you up for some maths?
Always.
Excellent. Let's see. So what we want is the mass of a polygon. So you recall that mass, let's get a sensible color, mass equals density times area. I say mass as like 2D mass because we're a 2D system. And we've got a fixed density, but we need to know the area of the polygon. Now, the way we work out the area of a polygon is, and I mean, you can like look this up on Google and stuff, but we may as well just do the actual maths for it. So say we have a polygon. Let's see, let's even a concave one like this. And the way we get the area is, let's say we're somewhere in space. Maybe that's our x and our y. And this is convenient because, you know, that's how we're storing these vertices anyway. And we take each line segment. So we take this first one. And we just, we don't so much project as we sort of just consider it as, okay, let's pretend that this line segment is a, what do you call this shape? Is that a rhombus? I can't remember. Is
Rhombish. It's not quite. I don't think it's quite a rhombus because it would have. No, I don't know.
I can't remember the specific.
Well, rhombus is sort of like the one where it's like leaning, right? The leaning rectangle. You've got one square end and one rhombesian end.
Okay, well we're going to Wikipedia for this. A rhombus is a simple all have the same length, so it's not a rhombus. Is it just a quadrilateral? You know what? It's now quadrilateral. I'm sure.
Yeah, that fits.
Oh, what's this one?
It's a regular.
I can't click it.
Yeah.
Oh, here we go.
Trapezium.
I think it's just a quadrilateral. I'm going to read this later because.
What is the point
here we
of
go.
naming all of these? Rhomboid.
I think it's it's a trapezoid. Anyway.
Yeah.
This is why I don't know, because who cares?
It's a polygon. It looks like it's the closest to a trapezoid than not being a trapezoid. So.
So what we want to do is we want the area of this shape. And so we can kind of think about the strategy we're going to use is, you know, we have...
yes. That looks like you just have to take this triangle and rectangle.
So I'm going to fast forward a bit, but yeah, that's more or less how you get the area of one of these sort of... It's a very specific kind of trapezoid because it's like these are 90 degrees and you know, only this side is angled. So it's actually trapezoid isn't explicit enough to describe this shape. So what we've done is we want to take the area of these two quadrilaterals, and if we redraw our shape now, that's more or less the shape we had to begin with. And if we have the area of this one, and hopefully you can see where I'm going with this one, this one. And if we add these two areas and we subtract these three areas, hopefully you can see that that's going to give us the total area of this shape. Does that make sense?
Yeah. I mean, I can see it.
Now, this is where winding order becomes important. So let's just quickly review how we get the area of one of these things, because it's really simple. You can imagine we have, let's pick a red color. If we have this shape, you can imagine that we could take the average of these 2 points on the shape and get a shape like this. And you can hopefully see that this triangle here is the same size as that triangle there. So we basically just stuck that one there. Make sense?
I mean, is that repeatable in the general sense, or?
Oh yeah, yeah, absolutely. So we've taken the average. So if that one comes up to there and that one comes up to there, if we take the average, we end up sort of here in the middle and just project that across.
Mm-hmm.
And then we have a rectangle, and we know a rectangle is simply width times height, and we can get the area by just being like, all right, the area is that. Yeah. So hopefully that makes sense. So we come down here and we're like, all right, well, we want to add these ones and subtract these ones. How are we going to do that? And the answer is pretty simple. It's this is point 1, point 2. We know that x1 is less than x2. So when we do x2 minus x1 equals width, we know that this is positive. If
Right.
we do the same thing here, if it's like 2, 3, 4. So we're doing, x of n plus 1 minus x of n. In this case, it's 4 and 3. We know that that is going to equal the width of this segment, and that's going to be negative. Yes. So in this case, we know that this one, x n plus 1 is greater than x n.
Now, why do we do this instead? Very vague memories of high school math are telling me why aren't we just taking the actual shape that we have, the blue shaded area, and just cutting that into as many triangles, doing the triangles?
Well, that's a thing we could do. However, that's a much harder problem to solve, because you can imagine, if we have a shape that's like that, that's the algorithm that has to work to be like, all right, let's divide this up into triangles. It's like, oh, we've got to do that. Oh, we've got to like clip off this bit because there's concave bits, and then we have to do that, and then clip off that bit, and that's 4 sides, so we have to do that. There's an algorithm that will do this. There's a few of them, but they're actually really quite complicated. And so that's a valid way to get the area, but if we do it,
probably going ahead, how does the way we are doing it get around the concave issue?
Well, hopefully you can kind of see that this is one of the nice. This is something you have to think about when you're doing sort of algorithms on polygons. It's like, does it work for concave polygons or not? And this is one of the nice cases where the algorithm actually works on concave polygons. It just works. And hopefully you can sort of see how that works, because we have a concavity here, but if I overlay the red and the green bits, hopefully you can see that that works. I mean, I could draw it so that it's say we had this was our polygon, which is concave, and
oh yeah.
Hopefully you can see that.
I see it. Yeah, I see it in the original image now. I actually made a mistake. What I did was, when I was thinking about concave, I was thinking about the fact that you've got curves in your jigsaw piece, and that's not the same thing.
No.
And I got confused by what I was saying. But yeah, no, I can see the concave in the example. I can see how you're basically eliminating it through like projecting these objects down and like cutting the concave part in half, and therefore making it not concave anymore, at least piece by piece. So I'm good. Other than I'll worry about curvy bits at some other time.
So that's actually raises an interesting point, because as you know, we were talking about this last time. We're like, okay, what if we have a compound shape like that that's made up of 3 pieces? It's like, oh, this area here and this area here, we're actually doubling up here if we just do like, well, shape 1 plus shape 2 plus shape 3. We've got these overlaps. And basically that's something that we'll have to figure out a way to deal with when we get there. Possibly the way that we deal with that is like, well, we don't care. We'll just set the mass of this directly. But we could actually try and think about, okay, here's where the overlap is. Let's subtract out this excess areas. So like if we know that we have that overlap. And we could do like a similar thing. You can imagine if we had a shape like this, we could get the area of the square and just like subtract out half a circle. But this is one of the cases, like depending on what you actually need from the algorithm, this could get quite complicated.
Okay.
But it's one of those like, well, we'll cross that bridge when we come to it.
Sure.
So we have our little algorithm here. So let's try implementing it straight up like this, and I think we might be able to come back and optimize it slightly, because you can imagine let's see, you can imagine we're doing width here, which is width is n plus 1 minus x of n, and then the next segment's going to be x of n plus 2 minus x of n plus 1. And so you can see that we're going to have this this term was going to appear like twice in the overall formula that loops through all of the vertices. So possibly there's an optimization we could do here. But first of all, let's just implement the simple way in code, because that's fairly simple. So we have a polygon. Let's do our lazy thing and just grab the code from, say, here that grabs all the vertices. So we have our from, we have our to, and we have this nice little thing where it like loops around. I'm going to change that to I just for funsies. One thing I didn't actually draw, but I just want to point out, and that is, and this is maybe something to think about, I don't know, afterwards, to sort of ponder on this, meditate on this, and that is that this algorithm works even if you're like below the the x-axis. So you can think about where these segments will be like you can imagine the average is going to be there. So that's something to sort of ponder upon, but it also works in that case, and it's sort of that's worth you just meditating on. So we don't need the shape position because the area is not going to change as we move this shape around, so we may as well not add that. So we want to take the average of the x and the y. So let me see. Float width is going to equal 2.x minus from.y. And thinking about it now, as I think about this, this is one of the nice things about having the vertices in a clockwise direction, because I think if you had them in a counterclockwise direction, you'd have to like negate the result to get a positive area. So hopefully you can see, in fact, that if our winding order was if our winding order was the other way around, if we were like 1, 2, 3 going counterclockwise, this algorithm would still all happen, but the these would be negative, for example, and these would be positive, and so we'd end up with a negative result because obviously these two are bigger. So this is why winding order is particularly relevant for this case, is we otherwise get a negative result. So height equals from dot y plus from 2 dot y times 0.5f, that's brackets. So that's precisely what we said, and then we just multiply them together. So we need to float area. Area plus equals width times height. And then we just return the area times the density. And we'll know if we made a mistake because our shapes will start moving backwards if they have negative mass. So let's give that a go, and let's see if if we make a huge triangle and make like a little tiny triangle. In theory, the little tiny triangle will move substantially, and the big triangle will hardly move at all. Excellent. So that looks like it worked. So that's how you get the area of a polygon. And yeah, for the time being, I don't think we'll optimize this. I'll just stick a to-do, and let's stick a to-do in this, because I think there is a way to optimize that, and I don't think we really have time to get into that, and it's not really worthwhile because I mean this is like dead simple. So I think
density is just like a game time factor. It's obviously we have no real material, so we don't really have a density.
Yeah, so we don't have density. So really, I mean, we could call this get area, but
that's fine.
We'll think about that later because it's one of the things. It's like we're building up to that. So just looking through this code, it's like what have we got left to do? I think the only... Oh yeah, we could do some culling on the radius. Might be worthwhile eventually, maybe. And then we have this allocation. We've got the optimization, we've got an allocation. So you can sort of see that we're getting the to-dos are down to like, fiddly things that while we're just, I guess, doing the sort of putting the big bricks in place, there's no real major need to do the fiddly little pieces while we're building the foundation. So I think that's where we'll finish up today. So thanks for watching, YouTube.